Today is the day we're going to prove that Cauchy sequences converge. In many ways, this is like the climax of the first part of real analysis. First of all, why is this something we should care about? Why is it so important? Sometimes when life is good, you have an idea what something is converging to. Something is getting closer and closer to the number 5 or the number 1/2 or the number pi, and you can study the error between your sequence and that supposed limit, and by studying that you can often prove convergence just using the definition of the limit. But what if you don't know what something is converging to? Maybe you're studying an infinite sum where you're adding more and more terms at each step, and you just don't know a priori what is converging to. You just want to know, does it converge? If you get lucky, if the sequence is, say, always increasing and bounded, then you can use the monotone convergence theorem, which would help you. But in the real world, that probably doesn't happen that much. So instead, this condition called the Cauchy property is something you can check just using the sequence itself. You don't need to know what the limit is. You don't have to have very strong properties like the sequence being monotone. And then this theorem that we're going to prove today shows that if you check this Cauchy property, you are actually going to know that the sequence converges. And in fact, if you read the proof, you can kind of see what that limit is. I mentioned it would take a while for us to prove this theorem. We could have done it a little bit faster, but I like waiting until we have the Bolzano-Weierstrass theorem from our last video, which really gives us a really tidy and I think satisfying proof. So the way that this proof goes is pretty simple. We take a Cauchy sequence, and we've proved earlier in our class that Cauchy sequences are bounded. And now, as of yesterday's video, we know that every bounded sequence has a convergent subsequence. It's very important that that subsequence, which I'll just denote always in the color blue, is going to converge to some limit L. And now we have a limit, a candidate for our whole sequence, the black sequence A sub n. We want to show that that sequence actually converges to L. And now the rest of the proof is that, well, imagine this original sequence, the black sequence A sub n. Now, eventually, because it's Cauchy, all the terms of the sequence are going to be close to each other. And so imagine you go that far down in the sequence, and now all the terms are going to be super close to each other. Well, some of those terms, in fact, infinitely many of those black terms are going to be blue terms. They're going to be in our subsequence. And eventually, one, and in fact, infinitely many of those blue terms are going to be really close to the limit L. And so now you just say, okay, well, take any black term in our sequence far enough down the line, it's going to be really close to all of the late terms. And so it's going to be close to that blue term we identified earlier. And then that blue term is, of course, really close to the limit because the blue terms are converging to that limit. Okay, I'm really out of the way now if you want to pause and read the whole thing. But I think what's most important is just this idea of using the Cauchy property to say the black terms are close to everything after some point, and so they're close to some blue term in the subsequence, and then all of those blue terms are definitely close to our limit because we know they converge. And also, thank you for your support in this video series. I never thought I could post videos about Cauchy sequences that would get thousands of views and really interesting comments. So thank you, and please keep the questions coming.